Good morning, dear students. In this lecture, I will design and analyze first order low pass Butterworth filter. Figure 8.2, it shows the first order low pass Butterworth filter that uses an RC network for filtering. Or we can say in this filter, we are using RC network. Note that op-amp is used in non-inverting configuration. Means in this figure we are using op-amp in non-inverting configuration mode. Hence it does not load down RC network. Register R1 and RF, it determines the gain of the filter. So we can say this is the filter, first order low pass Butterworth filter. Here this R1 and this RF, they will decide the gain of the filter. This is the R and C network which is used for filtering. Here we are applying the input voltage at the non-inverting terminal of the op-amp, that is V in, which is the input uh, voltage applied at the non-inverting terminal of the op-amp. This R and C, this is the RC network which is used for filtering. RL is the load resistance used, and this is the frequency response, or we can say the filter response at different input frequency. Up to a particular frequency which is known as high cutoff frequency, the gain of the op-amp, it remains constant, and after this particular cutoff frequency, the gain decreases at a particular rate, that is 20 dB per decade, and try to attenuate all the frequency beyond this high cutoff frequency. The frequency range from 0 Hz to this high cutoff frequency is known as pass band, and the frequency range beyond which the frequency attenuates is known as stop band. According to voltage divider rule, the voltage at non-inverting terminal, that is across the capacitor C, is given by V1. This is the voltage at node V1 is equal to minus j XC divided by R minus j XC, where XC is the capacitance of the capacitor into V in. Here we are using voltage divider rule, which we have already studied in previous lectures. Where j is, as we know, j is equal to under root minus 1, and minus j xc is equal to 1 upon j 2 pi fc, where f is the input frequency and c is the capacitance of the capacitor. Now if we simplify the equation 8.1a, V1 is equal to V in upon 1 plus j 2 pi RC, and the output voltage is, as we know, in case of non-inverting configuration, output is equal to 1 plus RF by R1 into V in. In this case, V1 is the input voltage applied at the non-inverting terminal at node V1. So we can say that V out is equal to 1 plus RF divided by R1 into V in. Put the value of V1 from the equation 8.1a V in upon 1 plus j 2 pi RC, and we can say that the gain is given by V out upon V in, which is equal to AF. AF is the passband gain of the filter, which is given by 1 plus RF by R1. So we can say this AF, in this case AF is 1 plus RF by R1. This is the pass band gain of the filter, and V naught upon V in is the gain of the filter as a function of frequency f. Now put the value of high cutoff frequency is equal to 1 upon 2 pi RC. This is the high cutoff frequency of the filter. Put this value, we obtained J is equal to F upon FH. So we can say V naught upon V in, which is the gain of the filter as a function of frequency, is equal to AF divide 1 plus J F divided by FH. FH is nothing but it is the high cutoff frequency of the filter. The gain magnitude and phase shift angle equation of a low pass filter can be obtained by converting equation into its equivalent polar form. That is, the magnitude of the gain is equal to AF divided by under root 1 plus F upon FH whole squares, and whereas the phase angle is given by minus tan inverse F upon FH, where FH, where phi is the phase angle in degree. The operation of the filter, that is low pass filter, can be verified from the gain magnitude equation 8.2a, this one. At low frequency, if f is less than fh, we can neglect this term and we obtain the gain of filter as a function of frequency is equal to approximately AF, that is pass band gain of the filter. At F is equal to FH, the gain is given by AF upon under root 2, which is equal to 0.707 into AF, means the gain at this frequency is equal to 0.707 times the value of AF. After high cutoff frequency, that is if the input frequency is greater than high cutoff frequency, the gain is less than AF, because this factor increases after a particular frequency, that is high cutoff frequency, and the gain is always less than AF. Thus, low pass filter has a constant gain AF from 0 to high cutoff frequency. At FH, that is high cutoff frequency, gain is 0.707 times the value of AF, and after high cutoff frequency it decreases at a constant rate with increase in frequency. That is, when the frequency is increased 10 folds, that is 1 decade, the voltage gain is divided by 10, or in other words, the gain decreases by 20 dB, because 20 into log 10 is always 20 dB. This is the formula for converting absolute value into dB. So we can say that if we increase the frequency, by a one decade, the voltage gain is also decreases by 20 dB per decade. Hence, the rate at which the gain rolls off after high cutoff frequency is 20 dB per decade or 6 dB per octave if we are increasing or if we are using the frequency in octave format, then in that case the gain decreases at a rate of 6 dB per decade, whereas octave signifies a two-fold increase in frequency. The frequency f is equal to fh is called cutoff frequency because the gain of the filter at this frequency is down by 3 dB from 0 Hz. The other equivalent terms used for high cutoff frequency are minus 3 dB frequency, break frequency, or sometimes it is also known as corner frequency. Now, how to design a particular filter? A low pass filter can be designed by implement the following steps. Number one, choose a value of high cutoff frequency fh. Suppose in that case, if we select a frequency of 1 kilohertz or 2 kilohertz or 3 kilohertz depending upon the requirement. Select a value of C less than or equal to 1 microfarad. Suppose if we select the value equal to zero point 0.1 microfarad, it's valid good. Malar and tantalum capacitors are recommended for better performance. These are the types of capacitor which are used to obtain a better performance. Now using the value of C and the cutoff frequency fH, calculate the value of R using the formula R is equal to 1 upon 2 pi fH C, or we can say fH is given by 1 upon 2 pi R C. In that case, we have the value of fH, we have the value of C which is selected by us, which is less than or equal to 1 microfarad, then we can calculate the value of R. AF is equal to 1 plus RF by R1. Once a filter is designed, there may sometime be a need to change its cutoff frequency. The procedure used to convert an original cutoff frequency fH to a particular new cutoff frequency is called frequency scaling. Is called frequency scaling. We can say that the conversion of original cutoff frequency to a new cutoff frequency is called frequency scaling. Frequency scaling is accomplished as follows. To change a high cutoff frequency, multiply R or C, but not both, by the ratio of original cutoff frequency to a new cutoff frequency. In filter designing, the needed values of R and C are not often standards. Besides, a variable capacitor C is not commonly used. Therefore, choose a standard value of capacitor. Then calculate the value of resistors for a desired cutoff frequency. This is because for a non-standard value of resistor, a potentiometer can be used. Suppose this is the example. If you are asked to design a low pass filter at a cutoff frequency of 1 kilohertz with a passband gain of 2. In that case, we have cutoff frequency fH is equal to 1 kilohertz. Now select a value of C which is always less than or equal to 1 microfarad. In this case, we are selecting 0.01 microfarad. After selecting the value of capacitor, select R which is equal to or given by the formula 1 upon 2 pi R F, sorry, CF, CFH, and we find the value as 15.9 kilohertz. In that case, we can use a potentiometer of 20 kilo ohms to decide or to adjust the value at a particular frequency of at a particular value of resistor at 15.9 ohms kilo ohms. Since the passband gain is 2, we can select R1 and RF equal. Therefore, let R1 is equal to RF, which is equal to 10 kilo ohms. So in this case, we have selected the value of R1, we have selected the value of RF, which are equal. If we put the value at this, then the gain of passband is equal to 2, which is the desired value. So we have find out the value of C, we have find out the value of R, we have find out the value of R1 and RF, put the value of R1, RF, C and R in the in this figure. We find the values and we have designed a low pass filter, first order low pass filter. So in this case, we have decided the value of R1 and RF equal because we are given the passband filter as passband gain as 2. That's why we have taken R1 and RF equal. In this case, first we have select the value of C, which is 0.01 microfarad. Then we calculate the value of R by using the given frequency, cutoff frequency, which is in this case it is 1 kilohertz. So after finding all the values, we put these values in this diagram, and this is the final circuit diagram for low pass, first order low pass Butterworth filter. In the next lecture, I will design a high pass filter, or we can say first order high pass Butterworth filter. Till then, bye bye, thank you, take care.